Thank you to the organizers for inviting me to speak. So I was told that the first talk should be more colloquium style, so that's what I plan to do, even though maybe many people are still in bed. So the setting for my talk is gamma is some sort of countable infinite group. M is always a compact manifold. And I'll always write diff superscript Rm for the group of CR diffeos So this is CR diffeomorphisms of M to itself. And of course, the operation is just function composition. And then what I'm interested in are actions of gamma on M, CR smooth actions of gamma on M. So that's just morphisms from gamma into this group. So alpha is an action of gamma on M. So that's just a morphism. And this is the sort of object I'm interested in. And let me say a little bit about some classes of groups. So there's some groups like Z, or the free group on N generators, or SL2Z. Okay. And morally, you're supposed to think of SL2Z as the free group on two generators. Up to finite indexes is true. Or maybe the fundamental group of a closed surface. So groups like this are supposed to be rather flexible. Whereas the sorts of groups that I'm interested in today are groups like SLNZ, where n is at least 3, or more general higher rank lattices, and I'll give a definition in just a minute, which are supposed to be rather rigid. So I really want to study actions of these groups on compact manifolds, say. And I really want to study actions of the rigid groups. So some motivation for why I might want to do this is that, well, I haven't told you what flexible or rigid means, but if you think in the world of linear representations of these sorts of groups have a lot of flexibility properties, whereas linear representations of these sorts of groups are very rigid. So my first motivation might be to extend rigidity results on linear representations. So linear representation is just a morphism to some linear group. Oops. To maybe the world of non-linear representations, which maybe by nonlinear representation, I mean a smooth action by diffeomorphisms. And maybe just to remind you of one rigidity result from linear representations, let me formulate a version of Margules superrigidity. Here's a theorem. And so this is a combination of various things that get called Margules superrigidity. And I'll stick to the group being SLNR today. So for n at least 3, and gamma, a lattice subgroup in SLNR. It's a lattice subgroup. So here's the acting group and I'll take a linear representation. So rho, a linear representation of gamma. So with all this data, there are, well, what I'd really like to say is that I can extend the representation of this group to a representation of the ambient group. So that's the first asserted object, is that there's a representation of the ambient group, SLNR, to the same target space. And I'd really like to say that rho is the restriction of rho hat, but it's not quite. There's an error, and the error is some compact group, K, inside of the target group, which is compact, such that if I take rho of gamma and rho hat of gamma, I'd like these to be the same, which means if I take the inverse here, I'd like this to be the identity, and it's not quite the identity, but it lands in K. So you can extend the representation up to some compact error. And then if you use sort of fancier versions of superrigidity, you can actually say what this K has to be. So moreover, this K, you can say what its Lie algebra has to be. It has to just be copies of SUN. And the appearance of the SUN is that SU is the compact real form of SL. So we'll actually use this in just a minute, the moreover here. So all the rigidity results, so local rigidity and Moss-style rigidity that you want about linear representations are subsumed in Margules superrigidity. And so you have results like this about linear representations, and can you say something about group actions? Can you say something about, maybe in quotes, nonlinear representations? And maybe my motivation too, I'll state it because this is actually sort of my motivation. I come from really the world of smooth dynamical systems and smooth ergodic theory. So if I just have a map from a manifold to itself, just a single diffeomorphism, say, just a diffeomorphism, I can just iterate this map over and over again. And from that, I can get some sort of dynamical data. And I won't be very precise about what I mean by that. But just there's lots of classical theories. You iterate a map over and over again, and you get some objects. And sort of going back to the world of group actions, maybe you could ask, how does the geometry of the acting group gamma, so constrain or inform so various dynamical data associated to an action of this group. And really, somehow our main theorem, one of the main theorems I'll say today is really in the flavor of this. I'm supposed to use this, then I'm supposed to figure it out. Okay, so that's sort of the setting. So let me get a little bit more precise. Give you some actual definitions. So just for simplicity, G will always be S, L, and R, so n by n matrices with determinant 1, and then there's a group structure by multiplication. Gamma will always be a lattice subgroup in G. So what does this mean? This means, i.e., gamma is a discrete subgroup. That's supposed to be a good approximation for G. So in this setting, that means that if I look at so G has a bi-invariant volume, and I can look at the volume of a fundamental domain, and I just want that volume to be finite. Okay, so these are the sorts of groups that I care about for today. A few other definitions. So gamma is co-compact. If, in addition to this volume being finite, if the quotient is compact, and then otherwise, we'll say that gamma is non-uniform. And I should give an example. And so gamma equals the integer points S, L, and Z. This is a non-uniform lattice in S, L, and R. So if you want, you can just think of this as the acting group for all of today. And a couple other definitions. So inside of G, I have my favorite subgroup, which I always call A. So A is a subgroup of G. And what is it? So it's a maximal R-split Cartan. And in this case, it's just the group of diagonal entries with positive, diagonal matrices with positive entries. So because we have the constraint that determinant is 1, this sum has to be 0. So there's n variables and one constraint. So this guy is, as a group, you can think of it as a copy of Rn minus 1. And so one last definition. So the rank of the ambient group G is the dimension of this group A, which is n minus 1. And so when n is 2, n minus 1 is 1. And so when we're looking at SL2R or lattices inside of there, those are rank 1 objects, which are supposed to be very different geometrically from higher rank objects. So I'll say that G is higher rank when n is at least 3. So squeeze that here. G is higher rank if n is at least 3. And the behavior of higher rank things versus rank 1 things is supposed to be very different. And my talk is about the Zimmer program, which is not quite so well defined, but let me give you some sort of philosophy behind various sorts of conjectures in there. So philosophy, this is sort of an overview of the Zimmer program. So if we have actions of higher rank lattices, so if n is at least 3, and gamma is a lattice subgroup, say in SLNR, then actions of gamma should, well, there's various flavors of conjectures you can put. They should be either, in some sense, rigid, or in some sense, they should be algebraically defined. algebraically defined. And I'm not being very precise because it's difficult to actually be precise here. I will be precise in just a minute. But maybe some evidence for why you might think such a philosophy is true is that, well, there's analogy with linear representations. Okay, but that's not, just because you have an analogy isn't great mathematics. There is a really important result, which is an extension of Margules superrigidity to a more general setting, which is due to Zimmer, which is Zimmer's cocycle superrigidity. Which at least gives some evidence that you should expect results of this form, at least for say, volume-preserving actions. And there's also a lot of work on local rigidity results of isometric and of affine actions. So I won't talk about local rigidity results, but there are results that really make precise what it means for actions to be rigid. And there's lots of local rigidity results for isometric actions or affine actions. So I've told you who my acting group is, and I've told you I want to look at actions, and I should give you some examples of some actions of these groups. So example 1, so of course you can always make a group act on a manifold by just making every element act by the identity transformation, which is of course kind of silly. You can make that a little bit fancier, but still keeping it silly by just taking your group and having it act by some finite group of symmetries. So let me write this down. So these I'll call finite actions. So if the image of your group, well, if your image of the group was just the identity element, we might call that a trivial action. If this is a finite group, then we'll say that the action is a finite action, or maybe almost trivial. And so, of course, you can build actions like this. But from my perspective, actions of finite groups are not very interesting. They're just some symmetries of the space. And at least coming from dynamical systems, we want things that have infinite orbits and have some asymptotic behavior to study. So let me give you some non-finite actions. And example 2 is projective actions. So let's take M. So here, again, we'll take gamma, any lattice subgroup in SLNR. And M will be the n-1 sphere, which I think of as the unit vectors in Rn. Or if you want, you can take it to be the projective space. And I'll build an action of gamma by nice, even real analytic diffeomorphisms. And what is it? So alpha of gamma applied to a unit vector x should be the linear action. But of course, that's not a unit vector, so you renormalize. And you can check that this is a well-defined action. So here's the sphere. Here's your point x. Here's gamma hit x. And of course, you just renormalize it so it still hits the sphere. So this is alpha of gamma of x. And if you think a little bit about the linear algebra here, if x is pointing in if x is an eigenvector for the largest eigenvalue, if you look at a neighborhood of x and look at what this does, this takes some volume around there and makes it a lot smaller under the action. So this is not a volume-preserving action. But it's also not a finite action. There's definitely lots of infinite orbits here, but this definitely distorts volume. Example 3, I'll call affine actions. And so here, I'm going to specifically take the integer points. So gamma is SLNZ. My manifold is the torus, the n-dimensional torus, which I think of additively. And so what's the action? I have an action of gamma by diffeomorphisms of the torus, Tn. And what is it? So alpha of gamma of a coset, x plus Zn, is, again, you matrix multiply. And you check that because this had integer entries in determinant 1, it preserves the cosets. So this is a well-defined automorphism even of the compact group here. And remark that SL means determinant 1, which means this preserves the Haar measure on the torus. So this is a volume-preserving action. The action preserves volume. And there's one more class, which I won't write out the details. They're in the notes. But I'll just give a outline. So I'm up to example 4, which is isometric. So I think the example I wrote out was if you let G be S, O, N, N, where n is at least 4, then you can find a co-compact gamma inside of G. And it has a representation. It's even an injective representation into SO. So the real form of this is SO2n. It's just given by a Galois involution. And this is injective. This is not a compact group. This is a compact group. So this has infinite image. And so this, of course, induces, this is the isometry group of the 2n minus 1 sphere. So then you have an action of gamma by isometries of the sphere of dimension 2n minus 1. And so I wrote out explicitly an example of this. I didn't write out explicitly what you do when you have an SLNR, because it's just a lot more algebra. But you can do this with SLNR, and then you get a map into SUN. OK, so I still have sort of a philosophy, which I'm calling the Zimmer program over here. And when I sort of say that an action should be algebraically defined, I sort of mean that it should it should be built out of examples like this up to there are some possible modifications you can do, but somehow underlying your action should be one of these examples. And if you believe such a philosophy should be true, and if you look at all these examples, so this is sort of the various algebraic constructions you can do. There's a few other. But in low dimensions, sort of example 2 and example 3 are the lowest dimensional algebraic actions you can build. So you notice there's some correlation between the n of the ambient group and the dimension of the manifold. And so the easiest to state conjectures are about actions and low dimensions. So this is bullet point 3. Actions in low dimensions. So with example 2 and example 3 in mind, and also just remembering example 1, state a conjecture. And this is usually called Zimmer's conjecture. And morally, it says that if the ambient manifold has dimension below the dimension which you could have any sort of non-trivial algebraic action, that all your actions should be of type example 1. They should all be finite actions. So I'll just formulate it for SLNR. If you want to see it for other groups, I formulated it for other groups. For n at least 3, gamma a lattice subgroup of SLNR. I won't keep writing that it's a lattice subgroup, but I always mean a lattice subgroup. And there are sort of two flavors of it. If I take a manifold whose dimension is below the dimension of the sphere or the projective space, so if it's dimension at most n minus 2, so I have a higher rank lattice acting on a low dimensional space, then every action by diffeomorphisms of M should be a finite action. And again, the reason is just because, well, we can't build any algebraic examples of actions, and if you believe the philosophy, then you shouldn't be able to build any sort of non-algebraic actions. And then there's part B, which is in dimension 1 more. If the dimension of M is at most n minus 1, then there's the action on the sphere, the projective action, but it's not a volume-preserving action. It definitely distorts the volume. So in this dimension, the conjecture is that every action of gamma by diffeomorphisms, but now I'll put a subscript, so VOL of M. So what I mean here is on M, I fix some smooth background volume form. I look at all the maps that preserve that volume form. So this is the volume-preserving maps for some fixed background volume form. Every action is also finite. OK, so here's a conjecture. And let me tell you a few remarks about this. So the bullet point B is actually what Zimmer proposed in the early 80s. He needed the invariant volume, at least for to apply co-cycle superrigidity, which gives evidence for why you should think such a thing is true. A is sort of a natural extension, and it appears in the first time I know of it in print is due to Farb and Shalin, which is around 2000. Most of the work on these sorts of conjectures are in rather low dimensions. So let me tell you about some known results. So when the dimension of M is equal to 1, so you're on the circle, or maybe the interval, there's a lot of extra tools you can use. And so for SLNZ, in groups like that, it's due to Dave Whitty. And then sort of in general, it's due to Gies has a proof. And then there's another proof due to Berger and Monod. And then when dimension is equal to 2, for the volume preserving case, there's work by Polterovich. And then for sort of general measure preserving case, there's work by John Franks and Mike Handel. And just in their work, they always need gamma non-uniform. And if you're an expert, they need unipotent elements inside of gamma to make their proof work. There's other work sort of for and very high regularity. So if you look at real analytic actions of non-uniform lattices, there's work from Farb and Shalin. And if you look at things like biholomorphic actions, there's work by Serge Cantat. But in terms of just the conjecture in general manifolds, just for actions by diffeomorphisms, the general work is, the only work, most of the work is in these very low dimensions. So let me give you a couple of other pieces of evidence for this conjecture. So one piece of evidence is, again, by analogy, is there's this corollary of Margules superrigidity, which says the following. For n at least 3, gamma, a lattice subgroup in SLNR, and D strictly smaller than n, every linear representation into GLDR. And so Margules says that you can extend this, well, but you can't have a representation of SLNR into GLDR, and you can extend it up to a compact group, but you can't fit the compact group in here. So every representation, linear representation, has finite image. So this is just by analogy, but you can sort of see this as a nonlinear version of that corollary. I think I want to swap these. And let me give you a slightly more sophisticated heuristic. Just the following. So if alpha is an action by gamma by volume-preserving maps of M, so now I'm assuming that I have an invariant volume. There's a corollary, and this is of Zimmer superrigidity, co-cycle superrigidity. And I won't tell you what co-cycle superrigidity is. I'll just tell you the corollary. And of course, here I still have gamma inside of SLNR. And n is at least 3. And this corollary says that if the dimension of M is less than n minus 1, less than or equal to n minus 1, then alpha of gamma preserves a measurable Riemannian metric. Okay, so what do I mean by this? I just mean there's a measurable symmetric 2 form on the tangent bundle. Let me give this a name, G. So this is true. And now there's a thought experiment, which is suppose that the measurable Riemannian metric that you get, you could promote to being C0. Well, that means that the image of your group sits inside of the isometry group of this metric. So, well, by definition, this group sits inside the isometry group of this metric. Isometry groups of measurable metrics, I have no idea what their structure is. But if this is a continuous metric, let me call this K. So if G is C0, K is compact, is a compact Lie group. And there's an upper bound on its dimension. So dimension of K is at most, I think it's m plus 1 over 2, where m is the dimension of m. OK, so there's definitely this is only a heuristic because we don't know that this is continuous. But if it was, then we have this upper bound on the dimension of this group. On the other hand, if alpha of gamma is infinite, then Margules superrigidity, or at least the one where you know about the compact images, would say that K, its Lie algebra, would have to contain an SUN, which would say that the dimension of K is at least n squared minus 1. And here's an upper bound on the dimension of K. Here's a lower bound on the dimension of K. And of course, there's a contradiction. If n is bigger than m, maybe if n minus 1 is at least m. So here's up to this assumption that we took something that was measurable and made it continuous. Here's a heuristic for why at least you should believe part B of this conjecture. OK, so I should tell you a theorem that's not 30 years old. So I still have the conjecture there, so I can tell you a theorem. So, which is due to me, David Fisher, Sebastian Hurtado, and the latest incarnation, we added Dave Whitty-Morris to it. And since the conjecture is still written there, even though it might be hiding, is the conjecture is true. And let me be a little bit more precise about this. So over here, I didn't specify the degree of regularity, partly because it's not exactly clear what you expect to be the sharp degree of regularity. So our result is conjecture is true for C2 actions, or even C1 plus holder actions. And we get the sharp conjecture for SLNR. And if you want to go for other groups, we get the sharp dimension bounds for R split Lie groups. If you want to be very fancy, we get the right dimension bounds for the R split Lie groups. And I was going to call this theorem A. And I think I'll erase the conjecture. So here's the conjecture. Our result is that the conjecture is true. And put a few remarks about this and about its proof. So there's going to be 3 papers, none of which are accepted yet. They should be sitting on referees' desks. So in 16, we did the co-compact case. And then in 17, we did the case of S, L, and Z. And then with Dave, we did the case for general gamma. And here you need a lot more reduction theory and reduction theory of arithmetic groups. And so we really needed Dave to come in and help us with that. So I should stop at 50, right? OK, yeah. So let me give you just like the very, very coarse sketch of the proof of this. And so to do that, I will tell you what is our real theorem, which is theorem B. And so I won't rewrite the hypotheses, but it's for an action of gamma by C2 maps of M as in the conjecture, which I've erased. Let's see, I didn't use the right word here. I want to say that every action has a property that we call uniform subexponential growth of derivatives. I won't write that out, but I'll just tell you what it is. So if we look at the derivative of alpha of gamma at a point x, and we look at how big this is, and we look at the sup of this over x and m, then we want this to be growing slowly in gamma. And so we want this to be growing like c e to the epsilon, and then here is L of gamma. And the quantifiers are for all epsilon, there should exist a c, such that the growth of the derivatives is sub-exponential. And what is L here? This is the word length. Of gamma. So you fix some finite generating set, and then you can measure the word length. And these derivatives should be growing sub-exponentially in the word length. So for every epsilon, there's some c. Of course, the c is probably huge. But how do you think of this result? Is that if you look on huge scales, where this word length is gigantic, then you can't tell the difference between this action and an action that was generated by things that were close to isometries, sort of how I think about this. That on huge scales, this action looks like maybe the generators were close to isometries. Of course, the individual generators might have size 1 billion, but at least on huge, large scales, it looks like maybe the generators were close to isometries. So let me just tell you the rest of the proof. So that's actually the main result of all 3 papers. And so how does the rest of the result go? So we apply something due to Vincent Laforgue and an improvement due to de La Salle, which just says that gamma inside of SLNR for n at least 3 has some property which is called strong T. And again, I won't formulate what this is. I wrote it out for, at least for Hilbert spaces in the notes. But essentially, it says that if you have an action on Hilbert spaces whose norm growth has this exact property, that you can find a fixed point. And so the corollary is that if our action has this property over here, maybe I'll call this property star. Then alpha of gamma preserves a continuous Riemannian metric. So there's a computation to do this, and I worked out the computation in the notes as well. And so then, of course, Margules will tell us that alpha of gamma is finite. So So the main result in these papers is this theorem B, which is some result in dynamical systems where we use the geometry of gamma to control the growth of the derivatives. If you know the words, this is actually saying something about Lyapunov exponents for all invariant measures over this action. So now I have 4 minutes, and I wanted to tell you another theorem. So let me see if I think I'll tell you another theorem at the beginning of the next lecture. But let me end by stating one new theorem, which we haven't written up yet, but we definitely have the proof of. So here's a theorem which is due to me, Federico Rodriguez-Hertz, and Jiren Wang. It sort of uses the results from our work on Zimmer's conjecture, which is for n at least 3, gamma a lattice in SLNR, and M a manifold whose dimension is n minus 1, and let's say alpha an action by C infinity maps of M with alpha of gamma infinite. Well, we know there's an example of such a thing. So there's the projective action on the sphere, on the n minus 1 dimensional sphere, or the n minus 1 dimensional projective space. And what we can show is that there is a C infinity diffeo H from M to either the n minus 1 dimensional sphere or the n minus 1 dimensional projective space, such that if you take alpha gamma of x and apply h to it, then that's the same as applying h of x. H of x is an element of the sphere or projective space, and so we know how to act on that. We have the projective action. And so in the first critical dimension, where you actually have non-trivial actions, where you have actions with infinite image, the only way that can happen is because you're the action coming from the second example. You're the projective action on the sphere, which of course double covers the projective action on the projective space. So with that, well, I think I'm 30 seconds short, but maybe I should stop here. And thanks for listening. Thanks for getting out of bed.
Questions?
Mm-hmm.
Somehow we step like everything goes to L, and there's a problem with that. That isn't rigid.
What happens if you go to a reductive group as opposed to a semi-simple group? And so I don't have a great answer. I think that usually you say these things for semi-simple groups as opposed to reductive groups, because otherwise you'll have a z inside of the lattice, or you'll have a factor onto z. And then, of course, you can, if your group factors onto z, then you can build all sorts of exotic things.
I have a question.
Yes?
So, sorry, it's very elementary.
Mm-hmm.
If I just look at a diffeomorphism and its iterate,
Yes?
can you give me an example of something that has more than polynomial but less than exponential growth?
Oh.
Because you said
Yes.
the special thing is that it's sub-exponential growth.
I don't have, I cannot give you an example right now, and I can't remember whether we know whether something exists or not. I've had this conversation, but I don't actually remember what the conclusion of it was. This is what we can prove, and that's enough for yeah.